Now we're going to look at some practical applications of trigonometric functions, in particular with angles of elevation and depression. So what is an angle of elevation? It's the angle formed by the horizontal line and a line of sight to a point above the line. The easier way to say this is it's the angle that your eyeball is going to create when you look up. So if you're looking straight out and then you look up, that angle that you make right there, that's the angle of elevation. So it is the angle you create when looking up. The angle depression is the opposite. It's the angle formed by the horizontal line and a line of sight to a point below the line. So now I'm going to be looking out horizontally, and then I'm going to look down. However big that angle is, that is the angle of depression. So depression is looking down, elevation is looking up, and it's always as if you're looking straight across as your starting point. So in example 1, we're trying to figure out which types of angles these angles are. I've got angle 1 here. So let's start with the guy in the helicopter. He's looking straight out. And if he's looking for the car, his eyeballs are going to go down. So if he's looking straight out, you can see up here, his eyeballs come down. So that creates angle 2. Angle 2 is the angle of depression because depression down. Angle 1 isn't actually an angle of depression or elevation because he's not going to be looking straight down if the car is way over there. So 1 is neither, and 2 is the angle of depression. Now we have the person in the car, and they're trying to sight the helicopter. Well, initially when they're driving, they're looking straight out on the road, and their eyeballs are going to move up. So if you look, that straight out is here, and going up is through angle 4. They're not driving around looking straight up and then coming down to look at the helicopter. So angle 3 is neither, but angle 4 is the angle of elevation. So some tips for problems. Again, you're going to use very similar strategies to what we did before. Draw a picture if necessary. It's not unusual to get these without a drawing. And then label the known sides and or angles. So you may know the sides, you may know the angles, so you might be using inverse trigonometric functions on these problems. Label the unknown side or angle with a variable so we can use it for our equation. Note if sides are the opposite, adjacent, or hypotenuse for the angle that you're dealing with. And then set up an equation with the trigonometric ratio that includes the knowns and the unknowns. And of course, don't forget, set your calculator to degrees. A person sights an airplane at an angle of elevation of 50 degrees. So angle of elevation, our eyeballs are going up. The airplane is flying 3,000 meters above the person. What they mean is that's the straight up distance from the ground to the airplane. That's not the distance from the person this way. What is the distance from the person to the airplane? So that's what they're looking for. They're looking for the distance from them to the airplane. So that's like a hypotenuse. I went ahead and drew a picture. See, there's the eyeball. Looking up 50 degrees, the airplane is 3,000 meters high. And how far is it from the eyeball to the airplane? So I labeled that with X. And that's the hypotenuse. I know the opposite. I know the angle. I'm looking for the hypotenuse. So opposite over hypotenuse is a sine trig ratio. So I say sine of 50 degrees is 3,000 over X. Now I want to solve for X, and I can kind of set it up so I can cross multiply it. I just go ahead and put a 1 under sine. And so I get X times sine of 50 is 3,000. I can divide both sides by sine of 50. And I get X is 3,000 over sine of 50. When I substitute that into my calculator, I get 3,916 and then a bunch of numbers. Well, I want this to the nearest meter, which is the ones place. So I circle the tenths place. That's a 2, so I stay where it is. And it's 3,916 meters. Example 3. Nathan finds a flagpole casts a shadow that is 25 meters long when the angle of elevation to the sun is 30 degrees. What is the height to the flagpole, to the nearest tenth of a meter? So you might be tempted to say, oh, a shadow, I'm looking down. But actually they said the angle of elevation to the sun. So if you were looking at the flagpole and you looked up, that's how far the sun would be. So let's go ahead and draw a picture. And here's my flagpole. There's the shadow. It's 25 meters. And the sun is back here, and it's creating this shadow. I know the adjacent of the angles at 25 meters. I know I'm looking for the opposite. And I know the angle is 30 degrees. So the function I'm dealing with is tangent. Tangent of 30 degrees is x over 25. This is actually very easy to solve. I can just multiply both sides by 25. And so x is 25 times tangent of 30. Entering that into my calculator, I will get 14.43 and a bunch of different numbers. I want it to the nearest tenth of a meter. So I underline the tenth position. That's a 3, so it stays where it is, 14 4/10 of a meter. Example 4. This is a really interesting example. You have someone who's partway up a building, and he's looking across, straight across at another building, and he looks up a certain angle, and he sights the top of the building just perfectly. When he measures the angle he has to look down to have the bottom, that's 55 degrees. So I drew a picture, and my 33 and 55 degrees are not perfect, and that's okay. It doesn't have to be to scale. So this is where the person is in this building. They're looking straight across. We know this distance is 25. There's the 33 degrees they look up to see the top. And there's the 55 degrees that they look at to see the bottom. I want the total height of the building, so I'm going to actually have to find A plus B. So we're going to start with the length of A. And I'm going to redraw this triangle to make it a little easier. So here it is, 33 degrees, A is the opposite, 25 meters is the adjacent, and 33 degrees is the angle. Opposite adjacent, that's the tangent function. So tangent of 33 degrees is A, and that's probably a little confusing because you might think it's adjacent, but I just chose A as a variable. And the adjacent length was 25. Multiply both sides by 25, and you get A is 25 times tangent of 33. I could enter into my calculator, but I'm going to go ahead and leave it as it is. And it's not a bad thing to leave it like that. Now I'm going to redraw the bottom triangle, and I have 25 meters and the 55 degrees in B. So tangent of 55 is the opposite over the adjacent, B over 25. I can multiply both sides by 25 like I did in the previous part, and I will find out that B is 25 times tangent of 55 degrees. But I want the whole height of the building, so I need to add A and B together. So I do that, and then when I enter these into my calculator, these are the numbers I get. I want to round to the nearest meter, and so I have 51.939. Here, I just went ahead and went out about 3 places. I didn't have to go super far, but I didn't want to cut it too short. Or you could have just entered the whole thing into the calculator at once. Make sure that you hit your parentheses when you're adding something to a trigonometric function so that it doesn't put this in the angle too. So my answer was 51.939. It said to the nearest meter. So I underlined the ones place. That's a 9 next to it, so I have to round up to 52 meters.